about reactions. Not what kind of reactions, but what's something else you can do about it. You can either write a full-on reaction like we have been writing, or you can write something called a net ionic equation, which is balanced, but it also shows really what's going on. So let's get into it. A lot of chemicals that we use are found in solid form and also in solutions. So what does that look like? Well, the solid lead nitrate exists as a compound, the lead and the nitrate stuck together. Whereas the lead nitrate solution really looks like this. The lead ions are separate or dissociated away from the nitrate ions. So lead nitrate really dissociates when you add it to water into a lead ion and two nitrate ions. Same thing with sodium iodide. Sodium iodide is stuck together in solid form, but then in a solution, they exist separate from each other. In double replacement reactions, one of the kinds of reactions that we can write a net ionic for, we need to worry about writing net ionics for anything that produces water and also for anything that produces a precipitate. All right, so notice down here at the bottom we've got some lead nitrate and some potassium sulfate, both of them solutions. Let's see what happens. The lead ions and the nitrate ions separate from each other. The potassium ions and the sulfate ions separate away from each other, and they form lead sulfate and potassium nitrate. The lead sulfate's a precipitate. The potassium nitrate is aqueous. So since this forms a precipitate, it's something that we need to worry about writing a net ionic for. So whenever we do double replacement reactions, we always have to check to see, does it make water or does it make a precipitate? And don't forget, it's always got to be balanced. Now, if you look at this one, iron chloride and copper 2 nitrate, it's going to make iron ions and chloride ions, copper ions and nitrate ions. It'll form, by double replacement, iron 3 nitrate and copper 2 chloride. Well, what would you put by the question marks? Are they aqueous or are they precipitates? Iron nitrate's aqueous because all nitrates are aqueous. Copper chloride is also aqueous. So what would we write? What kind of a thing would we write down for this? We'd write down no reaction. Because in truth, what happened? Well, you had some iron ions. You still got iron ions. You had some chloride ions. You still have chloride ions. You had copper ions. And over on the right still, copper ions. Nitrate ions. And nitrate ions. Everything's a solution. Nothing happened. That's not a chemical reaction. So we would write NR. We didn't make water. We didn't form precipitate. So no reaction occurred. Here's another example. You've got some sodium carbonate and calcium nitrate. They're both clear solutions. And when you put them together, what are you going to make? Well, you're going to make calcium carbonate and sodium nitrate. But it's kind of cloudy in there. So which one is it that is causing it to be cloudy? Well, it's the calcium carbonate because calcium carbonate is not soluble. The complete ionic equation, you would split up anything that's aqueous. So you split up the sodium ions and the carbonate ions and the calcium ions and the nitrate ions. And over on the right-hand side, you'd split up only the sodium ions and the nitrate ions. Because remember, a solid stays together. The aqueous thing splits apart. We can write a net ionic equation by basically canceling out anything that didn't change. There are spectator ions, things that don't change. We cross those two out because they're not doing anything. And we crossed them out there. Those are all of our spectator ions. And you're left with that. That, ladies and gentlemen, is a net ionic equation. And for anything that makes a precipitate, they really are very easy. Take the two ions that make a precipitate and you combine them together. It's just that easy. You really could have shortened this out. You didn't have to go through all that writing it all out and crossing it all out. You could have said, oh, I make calcium carbonate. So I'm going to take calcium ions and carbonate ions in solution and make calcium carbonate. It's just that easy. So let's mix together some zinc sulfate and barium chloride, both clear solutions. And when you combine them together, what happens? Zinc sulfate splits apart, barium chloride split apart. That's what's happening in those beakers. And when you mix them together, you get barium sulfate as a solid, because most all sulfates are aqueous except for barium sulfate, and you get zinc chloride. You can balance it, which is exactly what's happening here. And after you balance it, you got to start worrying about, how am I going to get rid of my spectator ions? There it is. Notice, take a long look, notice why I crossed out what I did so that we can practice it in class. So the net ionic equation is, ta-da! See, just that easy. Barium ions and sulfate ions makes barium sulfate. So what happens if you don't have a precipitate? Let's say you make water. Well, here's an equation. Took some sodium hydroxide and some hydrochloric acid, and in a double replacement reaction, they swap places. You make sodium chloride and water. So what do you do with this? Well, again, you split apart anything into its ions. So sodium hydroxide would split into sodium ions and hydroxide ions. Hydrochloric acid would split into hydrogen ions and chloride ions. And you would split apart the NaCl into sodium ions and chloride ions. But you would not split apart the water, because water doesn't split apart. You can go the long way and pull things apart and cancel out the spectators. But really, it's pretty easy if we just say, if we make water, that's because you're combining an acid and a base. And what did an acid and a base always make? A salt and a water. The net ionic equation is always hydroxide ions and hydrogen ions makes water. That's for every neutralization reaction where you have an acid and a base together. There is one more type of reaction that you can write net ionics for. These are single replacement reactions. We've got some solid zinc and some iron chloride solution. Now, you know, to check your activity series, is zinc more active than iron? Well, of course it is. So it will replace it. So they just swap places. How would we split these things into ions? Well, zinc isn't an ion. It's going to stay the same. The iron ions and the chloride ions, they will split apart. And then on the right-hand side of the equation, we would pull apart the zinc ions and the chloride ions, but you wouldn't pull apart the iron because it's just iron. So we split it into the ions. We write a full ionic equation. And then what do? That's right, we cross out the spectators. And when we cross out the spectators, what does that look like? Very good. Now notice you've got zinc on the left, and over here you got zinc on the right, but they're not the same zinc. The zinc on the left actually has its full complement of electrons, whereas the zinc on the right has actually lost 2 electrons. The iron on the left, it's got all of its electrons it started with minus 2. That's how it took on a plus 2 charge. So it's lost 2 electrons. And over on the right-hand side, notice it's no longer got a charge. That's because it's gained 2 electrons. So what happened overall? Well, zinc lost 2 electrons and iron gained 2 electrons. And that's really what it is. That's really what's going on. So why is chloride not important? Because chloride didn't do anything. It could have been iron bromide. It could have been iron nitrate. It could have been any ion that allows you to make an aqueous solution.